Hello, I'm Brian DiZio. I'm a first semester master's student in math, and I'm going to present homological features for sonar target classification. And so Janelle just gave a talk on the signal embedding theorem, and the reason we did this project, or Dr. Robinson chose to do this project, is basically based on the theory just proved by Janelle. So when you had your domain, your receiver domain, this can be characterized by things like anything you can take a measurement of. So water level, specific, because we did, I guess I should give a little reference or context. Ours is classifying things at the bottom of the ocean, basically from a submarine or something, using sonar. So when you think about sonar, you think of water level and angle that you take measurements at, and anything else that can characterize a signal. So you can use Doppler, which is the shift in frequency based on the movement of the transmitter receiver. And so the fact that you can pop it out and there's a one-to-one mapping between the receiver domain and the signal space allows us to classify. So the theory laid the foundation for the application. And Dr. Robinson observed that, well, I'm guessing, that synthetic aperture sonar, which is what we use, has all the conditions for the theory. So what we've been doing is, the first thing we get are a time series. So pulses, time, and the setup is, so to give a little more context, if this is the bottom of the ocean, you have kind of, this is sort of 3D. This is your cylinder. This is your, imagine coming out from the board kind of, right? You have a bar that has your transmitter and receiver moving along it, and it's transmitting pulses almost at a continuous rate, so really quickly. And it also samples those pulses, so the way synthetic aperture does it is it generates kind of a sonar view, so you get data from all of this range, which is dependent on the beam width, lots of other stuff. But, so that's kind of the setup you can imagine. And so as this moves along, you have a transmitter sending out beeps and a receiver collecting beeps. You get sound waves of different strength, like Janelle was saying, time of arrival. So you get all these pulses, right? So this is literally, you can kind of think of like, so you collect pulses from here to here, here to here. This is because the transmitter is moving here too. So this is a pulse at time 1, this is pulse at time 2, and so on. And so you're going to get a list of times of pulse. So this is the data we're given. So what we do next is transfer everything into a pseudometric space, because the techniques that are available right now use statistics, and we are going to look at a topological analysis. So the first thing we did was transfer everything into a pseudometric space using correlation distance, which is something we learned in point set topology. And basically what it does is the pseudometric is, it's like a norm or something like that with conditions on it that, I guess it's symmetric, the difference between 2 points is 0, and the triangle inequality holds. And the point is that there's a one-to-one mapping between the unique topological representations of the data here and in the here. So once we have it in the distance matrices, so what you can kind of see here is that we use the correlation distance. The distance between, you have pulses up here and pulses over here. So the pulse measure, the correlation distance of one pulse here is exactly the same as it is up here. That's why you get this diagonal crossing. And these are for different degrees because the target was rotated in the experiment. So that's why you have different correlation matrices. And the next thing we did was persistent homology. So we computed persistent, first of all, if you guys remember what we did in class, we took simplicial complexes and computed persistent homology or persistence diagrams from them. And the way we did that was through Viator strips. So we take all these data points that are in the pseudometric space and compute the Viator strips. And then you get, like all the data points have, you get some amount of complexes. And so you get, for each target, and for each angle that you're looking at, you get a persistence diagram. And it still has a unique topological representation. But now we're going to look at the homological features of the topological representation. So, like we did in class, you take the, what is that? We use the Wasserstein distance. So that's basically, you create a one-to-one mapping between all the little points in one diagram into another, and you want to minimize the distance between each one. So once you do that for each pair of targets, you end up with a confusion matrix. So I'm kind of rambling on a little bit, but the point is that these allow us to see how similar or different the homologies are of each target in a topological space. So you can see the homological features of the aluminum pipe and the aluminum pipe are, it's exactly the same because it has its own homology. So you can see that some targets look different from others. And what we're doing now, there's two things that are kind of cool that we're still doing, because I'm doing this with Dr. Robinson as we speak. And one thing that Jen is doing is, it was kind of problematic to compute via torus ribs, because you guys saw it takes a while. So we couldn't compute higher dimensional than, I think, 1 faces. So what we're going to try to do is kind of take a different sampling of this pseudometric space, so maybe not take all the data, and see if we can increase the dimension and then repeat this process. But something else we want to do here, so now we can see, okay, they look different, but we want to see how accurate results, how many times we'll get that they're different from each other. And so we're going to repeat this process and then do a statistical analysis on different representations of the confusion matrices. And the confusion, so don't, like, I wouldn't take the confusion matrix to be like a thing. It's more just like, that's the type of graph plot this is. And so that's what I think when I look at it. And so the other half of the project is that we want to simulate this whole experiment, because then we can control, right, and by simulate I mean write code that collects sonar data based on this acoustic setup with our own little simulations of the target. So that's the cylinder I made, and it's a bunch of discrete points that look like a cylinder, and he processes it into a time series. That is a statistical analysis, which I'm not going to get into right now, and then you basically do the same analysis. So, but the only difference is we're going to end up with this, but we can then control and mold every target. So we can see what exacerbates the homological features and maybe say, okay, well, you know, if we make this, right now it's symmetrical back to front, but if you get rid of that symmetry, then you can see a clear difference after all the analysis. So we can try to pick features of targets that help characterize them. And that's basically the crux of the whole project. Yeah, that's all. That's it. Thank you. Questions, Brian?
Yeah, sorry, so what does the color coding actually signify in the correlation and then versus the confusion matrices?
So what you have is pulses and pulses, right? So the color specifies the distance between them. So this is the pseudometric. When you compute the pseudometric, there is no distance. 0 is red.
Okay.
So that's why, you know, the distance between x and x in your pseudometric is 0.
Right.
So that's why you get no difference across there. But they are, so blue is higher and green is even higher, I think. I mean, I have to look at the color bar. No, green is high.
Green's the middle.
Green's the middle, blue.
Blue is highest, green is the middle.
Okay.
Yeah.
It's exactly reversed, sort of confusingly, in the other diagram.
Okay.
Yeah. But, yeah, so blue means there's no difference in homological features. Red means there is.
Okay.
Good.
So that leads to my second question. Do you know why there are weird, like, hotspots in graph C and graph D for your distances? Is that understood?
Well, yeah, so Dr. Robinson was telling me that you can end up with specular flashes. So the example he gave me was, so it's mainly has to do with when you broadside to a target, you get a ton of sonar energy. So it's like if I'm holding a mirror and the sun is right there, you're right there, right? So you're just looking at the mirror, you see stuff, see stuff, see stuff. Oh, then you get a ton of sun, no stuff, no stuff, no stuff.
Okay.
So those are possibly specular flashes.
All right.
Other questions? Great.